Hi, in this video we are going to see how we use the properties of the Fourier series expansions of periodic signals by means of two examples. Let us first consider a signal x1 of t is periodic with fundamental period t0 equal to 2. So we have a periodic signal with fundamental period equal to 2. And the following information is given related to this signal. Okay, x1 of t is real valued, so it's a real valued signal. The second information is the Fourier coefficients ak will be equal to 0 for magnitude k greater than 2. Meaning, for k greater than 2 or for k less than minus 2, the Fourier coefficients are equal to 0. The third information given related to this signal is A1 is equal to 1 minus j, and A2 is equal to j. The fourth information is the following. The integral of x1 of t from 0 to 2, that means over a period, is positive, greater than 0. And the fifth information is the following. 1 over 2 times the integral from 0 to 2 of x1 of t square is equal to 7. Okay. The problem is determine or the question is determine the coefficients ak. Okay. In fact, A1 and A2 are given, so we do not know A minus 1 and A minus 2, and also A0 is not given. So we are going to determine these coefficients by using the given information. Okay, so how do we solve this problem? The solution is as follows. Let us use the information given in the statement of the problem. x1 of t is real valued, so from the first statement, we know that for real valued signals, a minus k is equal to ak conjugate. Okay? So, this means that A1 is given as 1 minus j. So, from the property related to property of the Fourier series coefficients for real valued signals, a minus 1 is equal to 1 plus j. And similarly, a2 is equal to j. So this means that a minus 2 is equal to minus j, the conjugate of a2. Okay. Now, as you see here, we have no information about a0, but from 4, let us look at the fourth item in the problem statement. Now, a0 is equal to 1 over 2 from 0 to 2 x of t dt. So this is therefore from property or from the given information in item 4, this is greater than 0. A0 is, if a signal is real valued, A0 is of course also real valued because it is related to the integral of x of t, and x of t is a real valued signal, therefore the integral is real valued, so a0 is real valued. Okay. Now, item 5 is an expression related to the integral of the square of the signal over a period. And we remember Parseval's identity. We remember that by Parseval's identity for the signal x1 of t, 1 over 2, this 2 here is the fundamental period, from 0 to 2 x1 square of t integrated with respect to t is equal to an expression given in terms of the summation of the squares of the magnitudes of the Fourier coefficients. So we have a0 squared plus a1 magnitude or modulus squared plus a minus 1 modulus squared plus a2 modulus squared plus a minus 2 modulus squared. Now, from item 2, we know that ak is 0 for k greater than 2 or k less than minus 2. Therefore, the only terms are given here in Parseval's identity. We have only 5 Fourier coefficients. Now, remember that in general, even for real valued signals, the Fourier series coefficients are in general complex valued, except the coefficient a0, which is real valued for real valued signals. That's why here I didn't write a0 magnitude square. The others are modulus square because in general they are complex valued. Now, this expression is equal to the numerical value is 7. Therefore, this is equal to a0 squared plus, now a1 is 1 minus j. So what is magnitude of a1? It is real part squared plus imaginary part squared, square root. But we have also the square here. So it is real part squared plus imaginary part squared. So it will be equal to 2. A minus 1 is the magnitude or modulus is also equal to 2, and A2 and A minus 2, the magnitudes are equal to 1. So we have 1 plus 1. So this makes 6. Therefore, A0 square is equal to 1. And we know that A0 is real valued. And also we know that A0 is positive. So we obtain A0 as 1. Okay, so in this example, we have a certain signal and certain statements or information given for that signal. By using the information and by using certain properties of the Fourier series expansions, such as the symmetry relations for the coefficients of real value signals, and by Parseval's identity, we are able to obtain all the coefficients. In fact, we have 5 coefficients in this case: A0, A1, A minus 1, A2, and A minus 2. And we are able to obtain all of these coefficients by using the information given in the statement of the problem. Okay, now we are going to see another similar problem to understand the usage of the properties of the Fourier series. So now let us look at that problem next. Okay, now the second problem is very similar to the first problem. Again, we are given a periodic signal and certain information related to that signal, and we are going to obtain a certain value for a certain integral. We have such an application in this case. So x2 of t is a periodic signal with fundamental period t0 equal to 2 again. Okay, the first information is the following. x2 of t is real valued and odd. So it is a real value signal, but also it is an odd signal. That means x2 of t is equal to minus x2 of minus t. The second information is, again, the Fourier series coefficients are 0 for k, magnitude k greater than 2. That means for k greater than 2 or for k less than minus 2, the Fourier series coefficients are 0. So we have only A0, A1, A minus 1, A2, and A minus 2 as non-zero coefficients. The third information is A1 is equal to J and A2 is equal to 2J. Okay, so we have these items, statements given as information related to the signal x2 of t. Okay, the problem is evaluate the integral from 0 to 2 x2 of t squared. Okay, so this is our problem now. Now again, how do we solve this problem? Now, since x2 is real valued and odd, since x2 is real valued, first of all, x2 of t is real valued. Therefore, this means that a minus k is equal to ak conjugate, complex conjugate. So, a1 is equal to j. This means that a minus 1 is equal to minus j, and a2 is equal to 2j, and this means that a minus 2 is equal to minus 2j. Now here, we know that the signal is real valued and odd. Now, as you remember, for odd signals, real valued and odd signals, the Fourier coefficients are pure imaginary. So we observe this in this example as well. And also by using the important result related to real value signals, related to the Fourier coefficients of real value signals, a minus k is equal to ak conjugate, we are able to calculate a minus 1 and a minus 2 from a1 and a2. Now what about a0? Again, how do we calculate a0? Now a0 is, remember, equal to 1 over 2 from 0 to 2 x 2 of t integrated with respect to t. But we also remember that the Fourier, in the calculation of the Fourier series coefficients, we can integrate over any interval equal to a period. So this is also equal to 1 over 2 from minus 1 to plus 1. Instead of 0 to 2, we have minus 1 to 1, x2 of t integrated with respect to t. But we know that x2 of t is odd. So this is odd. That means x2 of minus t is equal to minus x2 of t. Therefore, this integral will be equal to 0. In fact, for odd signals, the coefficient a0 is always equal to 0 because of this expression given as an integral for a0. Okay. Now we can evaluate the integral which is given in the statement of the problem. We are required to calculate that integral by using Parseval's identity. By Parseval's identity, we have 1 over 2, the integral from 0 to 2, x2 squared integrated with respect to t is equal to a0 squared in general, but a0 is equal to 0. We have calculated that. Plus a1 magnitude squared, a minus 1 magnitude squared, plus a2 magnitude squared, and a minus 2 magnitude squared. Now, it is important that we always remember the following. For Fourier series coefficients, even for real valued signals, the Fourier series coefficients turn out to be complex in general. So in Parseval's identity, on the right-hand side, we have sum of the modulus squares of the coefficients. So this turns out to be a0 is equal to 0, a1 is j, so its magnitude squared is 1. Similarly, a minus 1 squared is 1. a2 is equal to 2j, so its magnitude squared is 4. And similarly, a minus 2 magnitude squared is also equal to 4. So this makes 8, 10. Okay, therefore, the integral from 0 to 2 x2 squared integrated with respect to t is equal to 20. Okay, so in these two examples, we have used certain properties of the Fourier series expansions or Fourier coefficients in general, certain properties of Fourier coefficients, and certain results such as Parseval's identity to solve two example problems. Thanks for watching.